Okay. So what we're going to look at today are ionic solids, or actually ionic substances, but we're going to focus on the solids. So ionic things are things like salt, sodium chloride, and actually we use the word salt to describe anything that's made up of a cation and an anion, so positive ion and a negative ion. So the particles that these things are made up of are called ions, not surprisingly. And the cations are the positive ones, that's why I always remembered it, so I've chucked it in there. T looks like a plus sign, so that's that one, and the anion's your other one. The book's got a really lame way of remembering that. It might work for you, it might not. And if we show as a model, it looks something like this. Now if we write sodium chloride on the board, we just write NaCl. But if you have a look at this model here, there's a lot more than one sodium. The sodium's the grey, just for your information, and the chlorine's represented by the green. There's a lot more than one sodium there, isn't there? And there's a lot more than one chlorine. So what this really is, it's a ratio of the ions. There's one sodium ion for every one chlorine or chloride ion, I should say. So if I have something like calcium chloride, which is CaCl2, it means there's two chlorides for every one calcium ion. It doesn't mean there's only one calcium ion and two chloride ions. There's literally billions of each of them. But if there's a billion calcium ions, there'd be 2 billion chloride ions. So these are a ratio. It's actually what we call an empirical formula if we're doing organic chemistry. All right? And we did that with the percentage composition. So if you have a look at it, if we look right in the middle rather than at the periphery, this is just a piece taken out. If you look right in the middle, every sodium is actually attracted to every sodium is attracted to 6 other chlorides. And every chloride is attracted to 6 other sodiums. So it's not just a case of one sodium being attracted to one chloride. It's actually in 3 dimensions, so in every direction. This is why sodium chloride and all other ionic salts are so strong, because they've got that very strong attraction, it's called an ionic bond, in between the particles, and right in the middle, every one of them is joined to up to 6 of them, 6 others. So it's really, really strong bonding. What that means is that it's got some very, very characteristic properties. So for example, what I'm going to try now is to actually try to melt it. But to give you a bit of a compare and contrast, I'm going to melt some sugar first, which is a molecular solid. So it isn't made up of ions at all. So I'm going to go to blue flame because I know that these things, being solids, probably take a fair bit of energy to do anything to. So the first one's going to be actually glucose, sorry, not sucrose and not sugar. And glucose has got carbons and hydrogens and oxygens in it. And let's see what happens when I heat that up. You can see it starts to melt, and eventually it will actually burn or boil. It'll probably burn before it boils. Okay, so it goes basically like toffee and then starts burning. So that's pretty easy. I mean, the Bunsen plate's not that hot, and that melted really, really easily. And it's a white powder you'd find in your kitchen. But another white powder you find in the kitchen is salt. And if we have a look at doing the same thing for salt, a similar amount, you'll see it looks pretty similar. It's just a white crystal. The same thing to salt, it doesn't do the same at all. It's not melting. In fact, I'm going to get a burnt hand before the salt does much at all. What you will notice is that yellow flame coming off it. That's due to something that happens with a lot of metals and a lot of metal ions. The ions go to what's called an excited state, and then when they drop down, they release a wavelength of light. In this case, it's an amber colour due to the sodium. But if we have a look at that, the salt hasn't changed at all. It's just a physical change. The electrons jump up, jump down, and nothing else. So the salt crystal can't be affected by that much heat. I'd need probably a couple of 1,000 degrees Celsius more to have any effect at all on that crystal structure. And that's because the bonds are so strong and there are so many bonds for each ion. Right, so that means that we know what particle type it is, and we know that it's got pretty strong forces. And these forces are created because these things in here, these ions, have gained or lost electrons, so become ions. The gaining and losing of electrons to make the ion allows that ion to create, not surprisingly, an ionic bond. And an ionic bond is an electric attraction, so it's a positive being attracted to a negative, or a negative being attracted to a positive. They are very strong. In terms of types of forces, they're right up there. So they're way more powerful than, say, gravitational forces, which are very, very weak. Electric forces are very, very, very strong. So you've got electric forces, which are these ionic bonds holding this crystal together. And again, you have to think of it in 3 dimensions, not as NaCl, but as billions of Nas and billions of Cls to really get that idea. Okay, so being held together like that also helps us understand a couple of other properties. Melting and boiling points must therefore be very, very high. Okay? But because these particles on the outside are charged, you can actually do something with salt that is quite cool. We can actually dissolve it in water. So I'm going to make a salt solution here. And that's because water is what we call a polar solvent. What that means is it's got a very slight positive side and a very slight negative side. So it can actually dissolve things. So if we actually put salt in there, and we can see the crystals, all I have to do is stir it to give it a little bit more energy, and actually allow the particles to collide a bit more, and that salt pretty much disappears. This is already a salt solution, so I'm getting it rather saturated. But even though those forces are really strong, the ones on the outside can be pulled off one at a time by water, because water has a slight negative and a slight positive. So I'll just quickly show you what I mean by that. Now I am going to show this as 1 Na and 1 Cl. If I've got Na plus, and then I've got Cl minus, and then these are bound to the rest of the crystal. Alright? If water comes along, water, the H side of it is what we call delta, lowercase delta, positive. And you'll find out more about that when you learn about molecular solids. And the oxygen side has got some lone pairs of electrons there, and also it's what we call a very electronegative element. So it's delta minus. So these two, this hydrogen side can actually attract the chlorine and pull it into the solution, breaking it away. At the same time, the slightly negative side of another water molecule is able to pull off that sodium ion. So it starts breaking the crystal down one ion at a time, basically. And that's what your dissolving actually is. Alright? Question?
In electrolysis, do they pump
Electricity?
Yeah.
Yep.
Water, and the hydrogen comes out, that's because it's water that was charged to.
Kind of. It's in pure water. Even in pure water, you have a very low, very, very low concentration of hydroxide ions and hydrogen ions. That's the hydrolysis part. I'm about to get to that actually, so I'll leave that idea just for now. Okay. Hopefully I'll answer it in a minute for you. Right, so in solubility it's just been pulled one ion at a time from the edges, basically, and that's how the crystal dissolves. Can't dissolve the whole thing at once because that whole thing's neutral. All the positive charges and the negative charges cancel each other out. Okay, and the last thing I wanted to look at was electrical conductivity, which links a little bit to that question we just asked. Okay. For something to conduct electricity, it has to have charged particles that are free to move. Sodium chloride or any ionic substance has got charged particles. That's what ions are. That's why the electric forces are holding it together. But they're held so tightly they can't move. So that means that the solid won't conduct electricity. But if we were able to break those bonds those are going to be free to move. So if I was able to get that salt hot enough to melt it, it would then conduct electricity, because then the ions are free to move. Charged particles moving is an electrical conductor. So, as a solid, they won't conduct. No way. When they're molten, so melted, then the particles are free to move. So it does. But what about if we have a solution? What I'm going to show you here is we've got some distilled water, so it's pure water, nothing else dissolved in it, so no solids in it. And I'm just going to quickly show you that there's nothing wrong with the lamp. If I touch those two electrodes together, the light bulb goes. But if I put it in distilled water, which is a molecular substance, even though it's got these polar molecules in it, it doesn't turn the light bulb on at all. But you guys saw that I made this a salt solution before. Let's see what happens when I put it in there. Okay, whoops, actually touching, so it's me cheating. Now I'm not cheating anymore. Okay, so I just have to make sure the two electrodes weren't touching, and you'll see that the light bulb's going not as well as when I do this, but pretty close. So that tells us that this very saturated salt solution is quite a good conductor. It's one of the reasons why when there's a lightning storm they tell you to get out of the swimming pool. Because if lightning hits that swimming pool, it will conduct that electricity through you like you wouldn't believe. Because there's dissolved salts, ionic salts in the water. Same thing with the ocean, but the ocean's not quite so dangerous because it's so big. So the chances of you being struck close enough for it to conduct through you are quite low. But in the swimming pool, the chances are a lot higher if there's a lightning strike. The last thing I want to go through is a thing called electronegativity. Oh, sorry, I forgot one here. So, solutions also do conduct. Solutions conduct because, again, those ions have been ripped out of this and are free to move. Right? Charged particles that are free to move. And the last thing I want to look at is a thing called electronegativity to decide whether something is actually ionic or not. Electronegativity is a measure of the attraction for bonding electrons. Right? So it's how tightly, basically how selfish an atom is, or how selfish a nucleus is. So fluorine is the most electronegative element. It's got a small radius, for its size, got a very high positive charge in its nucleus. So when it bonds with anything else apart from fluorine, it holds on to the electrons tighter than the other atoms can. So we give it a value of 4 on a scale of 1 to 4, called the Pauling scale. Sorry, 0 to 4, on a thing called the Pauling scale. It's the most electronegative. If you go the opposite way on the periodic table down to francium, you get the least electronegative element. I'm sorry, I can't remember the number. It's around about 0.4, I believe, for the lowest electronegativity. So that element has a very weak pull on the electrons when it's bound with something else. Ionic substances have an electronegativity difference. So when I take one atom's electronegativity and subtract the other one, of greater than 1 point, which no is here, that's greater than 1.6. Around about 1.6 it gets into a bit of a grey area. 1.7 definitely is. So if I look at sodium's electronegativity and I look at chlorine's electronegativity, the difference is going to be bigger than this. Alright? So I haven't got those numbers really just yet, so that's something we'll get to do later. Yes. Sorry, I'm going to do it for you now.
So is that heating the water?
Sorry? It will heat the water, and what it'll also do is it'll turn the chloride into chlorine if it's concentrated enough, but not enough to do us any damage. So no, there's not enough current in there, to be honest. If I put a big enough current, it could do us a bit of damage, though. Okay, the electronegativity of sodium. Sorry about this. Sodium has got an electronegativity of 0.9. And chlorine's electronegativity is 3.0. So when they join together to make sodium chloride, the difference is 2.1. Because that number is bigger than 1.6, we know that this is actually an ionic bond, not a covalent bond. Alright? So electronegativity is a really good way for us to determine whether something's got ionic bonds or covalent bonds in it, as well as looking at the typical properties like melting point and boiling point and electrical conductivity. So use all that evidence together to determine whether something is ionic or not.